So today we have Chris with us to present his paper, The New Geography of Breakthrough Inventions. And Chris, the floor is yours.
Okay, well, thank you very much for getting us started, Carolyn. Also, thanks for everyone for joining us today. I'm excited to present. This is really a work in progress. So, I'm looking forward to your feedback throughout, and I'll pause on a couple of slides that you can kind of voice some feedback also as I'm going. So hopefully it won't be too much material all at once. There's really three things that I want to do through this talk. The first one is that I want to think about breakthrough innovation. And I want to set up a definition of breakthroughs that I think is going to be useful. And in this regard, thinking about breakthroughs, I'm going to be defining breakthrough inventions as inventions that are both useful, meaning that they're impactful and have a practical application, but they're also novel, meaning that they deviate from the status quo to some extent. I think as you look at a lot of the literature on patents and impact, we've either gone after useful inventions in and of themselves, for example, looking at forward citation counts, or novelty in and of itself, and we haven't really put the two together. So for breakthrough, I think that both criteria have to be met. So I'll talk more about that as we go. After setting up a definition of breakthrough inventions, what I want to do is kind of describe the broader historical contours of what I call the geography of breakthrough innovation over the 20th century in the United States. By saying the geography of breakthrough invention, what I'm really talking about here is to what extent is the production of breakthrough inventions concentrated in space or dispersed across space? So kind of like the agglomeration of breakthrough innovation. And to prelude the kind of descriptive results that I'm going to share with you, I pick up that there's three distinct periods in the United States in terms of this geography of breakthrough innovation. So point A, during the early part of the 20th century, my data are telling me that breakthrough inventions were invented primarily in big and in particular knowledge diverse metropolitan areas. So a kind of traditional story of agglomeration. I pick up this kind of separate period in the middle of the century. This is from 1945 to 1960 roughly, where I pick up that breakthroughs started to be produced first off in smaller cities as well, so a greater spatial evenness. But the second thing that I pick up is that novelty overall was just less rewarded, less important during this period in the middle of the century. Basically novel inventions and incremental inventions were of relatively similar impact level, same usefulness during that middle of the century. So then fast forwarding to the very end of the century, so from about 1960 onward, I pick up that, again, breakthrough inventions are invented in big, knowledge diverse cities. So another kind of return to agglomeration. But there's a second thing that happens later on. And it's that those breakthrough inventions are not just invented in the big knowledge diverse cities, but also along the edges of intercity collaborative networks. So it's kind of like one big city is not enough anymore to invent a breakthrough invention. Those inventions are happening when you have multiple inventors located in two major cities or more who are collaborating together on the same patent. So that's goal 2 is I want to kind of describe some of those patterns. And then goal 3 is I want to offer an interpretation of this third geography, the 1960 to 2000. So I want to offer some sort of explanation for why I think that's happening. On point 3, this is where I'm still kind of the fuzziest. So I'm going to, whatever feedback you have on this is going to be very, very helpful. The explanation that I'm going to provide in this talk is that there's really 3 things that changed as we entered the late 20th century, and they have given rise to the new geography of breakthroughs that we kind of see persisting today. The first thing that has changed is that there's been an increasing need for inventors to draw on existing knowledge when creating impactful novelty. Now, this seems like it's a little bit contradictory that inventors need to build on more prior knowledge in order to introduce novelty that's impactful. If it seems kind of strange, it's because novelty often suggests that we're breaking from the past. But if you think about, for example, the Brian Uzzi's paper in 2013 about how the really impactful novelty adds an element of novelty to otherwise traditional material, that's kind of what we're looking at here. And that's relatively a new outcome. The second thing that I think helps to explain the new geography of breakthroughs is that there's an increased ability today, or in the late 20th century, for teams of inventors to collaborate over long distances. So the evidence I'm looking at suggests that collaboration across distance is not really a major barrier to inventing breakthroughs today, perhaps compared to as it had been in the past. The third trend that's going on is that there's a persistent advantage for sourcing knowledge in places where you have presence. And in this regard, what I'm saying is, I find that teams are able to source knowledge from the multiple locations where their people are scattered, but they're not very effective at sourcing knowledge where they do not have people in the team on the ground. So multi-locational collaboration is working, but long distance knowledge sourcing isn't working. And those teams are expanding across space to be able to source knowledge from different places. So these are the three factors, and we'll come back to it, that I think help to explain this, the emerging, the spatial patterns of breakthrough innovation that emerged over the late 20th century. And so we'll come back to all of that. I'm going to start though with goal 1, where I'm just trying to set up a definition of how I see breakthrough inventions as the intersection of usefulness and novelty. So I want to start out by talking about incremental inventions, novel inventions, and impactful inventions, and I'll talk about those independently, and then we'll start to put the three together. To begin with, incremental inventions, these are generally, we would think of these as inventions that improve on existing technologies in predictable ways, because we tend to think of incremental inventions as being relatively banal, kind of meaningless or trivial. But they can also be wildly successful. And I think because, examples like the iPhone 12, for example, tells us that we shouldn't just assume that incremental inventions are of low impact. I'm going to go to patent data from the US Patent and Trademark Office, granted between 1900 and 1999, and identify the patents that are incremental. And to make this identification, I'm going to turn to Z-scores. This is a method that's pioneered in patent data, I believe, by Brian Uzi's paper, but has popped up in a lot of research since then. And what a Z-score does is you look at the individual subclassification codes on a patent. Those roughly correspond to the technological fields or technological elements of that patent, of the technology itself. And the Z-scores look for atypical combinations of those elements. An atypical combination is a combination of elements that is not predicted based on past combinations evidenced through earlier patenting. So an incremental invention is one that includes combinations of subclasses that have already existed in kind of high frequencies over the past. So I'll build up these Z-scores for all the patents, and using them, I'm able to identify incremental inventions. My definition here is kind of in keeping with the literature on patents that's doing this. The second thing that I want to define is novel inventions, which are, in this case, the opposite of incremental inventions. Quite straightforwardly, novel inventions deviate from the status quo. And in and of itself, novelty implies just that and nothing more, deviation. We often think that deviation is, it's often carried as like the lone kind of force for technological change. But of course, most deviation is unsuccessful. And most novelty is actually going to be inferior to the status quo and will likely fail. So once again, there's going to be heterogeneity amongst novel inventions in terms of their impact or usefulness. Nonetheless, putting that aside, I can identify novel inventions, turning to the Z-scores again, and looking for patents that introduce one or more atypical combination of subclassification codes. So the last thing to talk about then is the impactfulness of inventions. For me, this is inventions that introduce new knowledge that becomes used and reapplied in many subsequent inventions. So it's useful for subsequent innovation. In terms of identifying the impact of inventions, historically, I need to create new data because we don't have very reliable impact indicators before 1975 when we first get patent citation records. So for identifying the impact of inventions, I'm going to turn to a data set that I created and discussed in an earlier paper that is now up on a working paper, where I basically built a tree of technology using patent records so we can trace the flow of knowledge between patents over time and study the patents that have outsized impact on subsequent invention. To illustrate very quickly how this method worked, I'm basically taking a universe of patents. So here's an example of 7 patents that you can see here. And using the USPC classification codes on them, I'm making predicted inheritance structures between those patents based on shared classification codes between individual patents. So if you look at, for example, patent 2, P2 here, it has a classification code of A, as does patent 1. And because of the time ordering of the grant dates of those patents, I'm making an inference about how knowledge flowed through this to then create this sort of technology tree. If you're looking for, I don't want to spend too much time on this right now, maybe in Q&A as we come back to the end, I can answer more questions about this, but I do describe the full method that I used to create this and also discuss some of the kind of validation checks on the data in a working paper that's public online. So you're welcome to take a look at it there. Once you have this tree set up, it's very much like having citation records for every patent in that you're able to then go in and infer which patents are more impactful on subsequent patenting. For example, patent 2 has 2 knowledge-based descendants in the tree, while patent 3 only has 1. So we can infer that patent 2 is more impactful than patent 3. So once we've arrived at a definition of impact using this, we can start to put novelty and impact together, start thinking about breakthroughs. And then this will be the last slide before I break for questions. That's what I do in this slide. The point of this slide is to help you think about these 2 in conjunction. So this is a 2x2 matrix where patents are allowed to vary in terms of their degree of novelty. So we have incremental patents that do not introduce atypical combinations, and novel patents, those that do introduce atypical combinations. And then I have patents grouped by low impact patents. In this case, I've used a binary cutoff for impact to set up a 2x2 matrix. And we have high impact patents. So that sets up 4 different categories of patents. In the first category, we have incremental patents that are also of low impact. I'm calling these really failed conservative experiments. You set out to do something kind of simple, and unfortunately, it still didn't work out. Most patents, according to my calculations, fit this criteria. So between 1900 and 1999, 72.4% of all US PTO patents were, according to my data, failed conservative experiments. You also have incremental improvements. These are instances where you set out to do something relatively simple, but you really succeeded at that. And so about 6% of patents fit that criteria. You also have failed radical experiments. So you tried to do something crazy and you did something crazy, but it wasn't productive. And so, it's maybe not that useful nonetheless. In this case, you have about 19% of patents fitting that criteria. And then you have the final category, and I think this is the one that we're really interested in, right? These are the ones that set out to do something different, and they succeed in doing that. So I call these the breakthrough patents, and they correspond to about 2.7% of all patents in my data set. So where we're going to go from here is start talking about cities and geography, but I know I just shared a lot of information, so I'm happy to take any questions about the material up to this point.
How do you define a combination, Chris?
So fantastic. So let me back up a slide to look at this one. Let's take patent 2 as an example. Patent 2 contains 3 subclassification codes. In this case, I'm working at highly disaggregated level. There's 10,000 unique codes. And so patent 2 contains, for the purpose of generating Z-scores, it contains 3 different combinations. It contains a combination of A and C, a combination of A and E, and a combination of C and E. And so for computing atypicality, I'm looking for if those have been used frequently together before in combinations.
Okay.
and that's in keeping with the literature of kind of Muse's study on z-scores, but also the Brooks-Gaetani piece.
And so you're looking at the frequency of those combinations as a measure of novelty?
Yeah, so how the z-scores work is it's the frequency minus the expected frequency, and the expected frequency is the number of occurrences of the individual components.
Right. Okay.
So there's a normalization for expected in that calculation as well.
Makes sense. Okay.
Chris, Kirsten had a question as well, and she was asking about the ancestral tree. How are the patents related? Do they cite each other, or is this simply ordering them by priority date?
So these are ordered by grant date, and then the matches come through identifying shared knowledge between the individual patents once they've been ordered by the grant date. So you can see on this example tree, for example, all the patents are ordered sequentially through time, but then the actual edges, the predicted edges that the method is generating are between patents that have similar knowledge as evidenced by combinations of subclassification codes. Does that clarify that? Hopefully that helps.
So say P4 would have cited P2, is that right?
Yeah, yes, exactly. So we don't have citations, right? These are predicted knowledge flows, but that's the idea, is that knowledge flowed from P2 to P4, and I'm making that prediction based on the shared classification codes of those patents and their grant date.
Why the
so
grant?
P4 would have had the same, sorry, Chris, Ryan, sorry.
No, you go ahead, sorry.
Like P4 would have the same classification as P2, like the same combination of subclasses?
Exactly, or similar combinations. So in this case, I identify that P2 contains the subclass A, and P4 contains the subclass A. So that's what's drawing the edge in this case. In the data, how it works out is what matters is not just having individual subclasses, but combinations of subclasses, because those combinations are, they're more rare, so they really help to predict the edges. For example, P2 to P5, we see a C and an E in P2 and a C and an E in P5. So the inference that I make is that P5 drew the C from P2, it drew the E from P2, and it drew the C and the E from P2. So there's kind of 3 units of knowledge that were drawn from P2 by the inventors that made P5. So again, the full kind of elaboration on the methods are up in the working paper.
Thank you.
Why are you using grant date, Chris?
So great question. I ideally would use an application date or something earlier than a grant date, but because I'm going back to, in this data, going back to 1850, and in terms of analysis going to 1900, we don't have application dates back to that date. So grant date's the best estimate you have.
Can you not get the publication date of the original application?
So the original application, I think that data goes back to 1960s. I'm not sure on the time, but you don't have a long time series for application dates.
Got it. Okay.
Something that is helpful is as you go back, you might be concerned, okay, some patents were granted after the knowledge was generated. You'd be right about that. As you go back in time, this tree becomes more sparse. So you have fewer instances of patents flip-flopping. So the earlier data I'm a little bit less concerned about in terms of that flip-flop. But yeah, I would ideally have a much better timestamp on this of when that knowledge was first actually generated or an application applied for.
Got it.
Working with what I have here. Should I push along?
Yeah, I think so.
Okay, thanks.
I had another question, but I think I'll wait for it.
Okay, fantastic. Well, thanks. Those were great questions. So what I wanted to kind of return to now is we're interested in these breakthroughs, but we're interested in where they're invented and how does their location change over the course of time. So let's talk a little bit about locations then. So let's back into cities. With cities, what I'm going to emphasize here are some cities vary for me in the meaningful dimension based on the diversity of the knowledge stock that's circulating there. And knowledge diverse cities are important because in these locations, inventors are able to source a wider range of ideas through face-to-face communication. So through a kind of efficient communication technology. What this means is that inventors in knowledge diverse cities are more able to source knowledge that might make an atypical combination. Simply by the breadth of knowledge going around there, there's a higher probability that some of those combinations you make will be atypical. But I want to add to this also that they're more able to make combinations that are made between complementary atypical components. So this is kind of moving between just not having novelty. So atypicality can imply novelty, but complementary components is necessary to have a useful, practical, and impactful invention. So this is why knowledge diverse cities should be relevant in this regard. How am I going to define the knowledge diversity of a city in this case? Well, I'm going to look at metropolitan areas which produce patents in a wide number of USPC subclassification codes. The technical definition is that a city has to produce patents that are assigned to 10% or more of all the USPC subclass codes that are assigned to all US patents in a given half decade. So I'm allowing the diversity kind of, the diversity criteria of a city to be a diverse city to vary depending on how diverse the entire patent stock of the United States is in a given period of time. You know, when you look at the data, about 20 cities on average out of about 900 end up fitting this criteria. I move it around and I find that, you know, it doesn't really change this result substantially. So with that set up, let's start to look at where breakthrough inventions are made. Are they made in knowledge diverse cities, or are they not? You know, is there no kind of spatial relationship between breakthroughs and the diversity stock of a city? So here's the first results table that we'll look at, and this is kind of plotting the raw data. And we have on the y-axis the average impact. So this is the number of knowledge-based descendants. It's kind of like the average forward citations, if you will, but using my predicted tree of different types of patents across years. So in the green line, we have novel patents that are produced in knowledge diverse cities, right? In the orange line, we have novel patents that are produced in knowledge homogeneous cities. Homogeneous, I don't want to use the word specialized, but homogeneous seems to capture more that there's just not a breadth of knowledge stock in that location. In these, I guess I would call them blue and purple. In blue, we have normal patents. So these are incremental inventions, normal, incremental, synonymous here, invented in knowledge diverse cities, and the normal inventions invented in knowledge homogeneous cities. So the kind of, I would say there's really two takeaways here. One is that the average impact of all inventions is increasing over time. That's maybe not so interesting. But what is more interesting is that you start to have a departure as novelty invented in the diverse cities starts to become much more impactful than novelty invented in knowledge homogeneous cities. Now, there's really two key issues behind this chart that I have to deal with now. One is that all of these charts are rising as a function of time. So I need to do some kind of controlling for the kind of, if you will, like impact inflation over time. But the second is that the method I used in matching patents to their knowledge-based descendants, it assigns more descendants to patents that contain many subclassification codes, kind of by virtue on just those patents having many subclassification codes, because then they'll have more combinations of codes, and then they'll have more knowledge-based descendants as well. So I want to control for those two factors, the number of subclassification codes on a patent and the number of, and the time period that a patent is granted by. So what I'm going to do is I'm going to basically do a big deflation exercise where I'm going to take a model of the impact of individual patents. I'm going to regress it against this factor variable that controls for the number of classes on a patent and the time period that patent is granted in. Here it's by half decades. And so that's going to demean all of the impact values based on the average level of impact of patents of a given number of subclasses during a given period of time. Once those are demeaned, these beta coefficients for novelty, city diversity, and the interaction of novelty and diversity, I can then take those beta coefficients and reproduce these historical trends with those control variables in place. So let me show you what this looks like once you've done this. Here I'm basically now using with those control variables, making the same chart. And I think the results are also a little bit more interesting, and I would say probably, I think, a little bit more trustworthy as well. To begin with, we see that novelty, inventing diversities, was highly impactful early on. And then we see this decline in the impact of novelty in the middle of the century, right? Introducing a novel patent was no more helpful for making a high impact invention than introducing an incremental invention in the middle of the century. But as we move toward the end of the century, we start to see a big departure as novelty invented in diverse cities starts to become highly impactful. So these are the breakthroughs are now being produced in diverse cities. And we see that the novelty invented in knowledge homogeneous cities is just declining throughout. To this point, if you're in a homogeneous city, you're probably best off not trying to do something that's particularly novel. So these curves start to then, I think, really speak to the story of that novelty is now much more of a knowledge diversity, or breakthroughs are much more of a knowledge diversity outcome than they had been in the past. Let me see if there's any questions up to this point.
Yeah, can I ask a question about this graph?
Yeah.
So does that mean that all of these lines are converging around 1950? Does it mean that there were basically no very impactful patents in the 50s, or was it that the impact of all, like, doesn't matter where you're patenting, the impact is sort of the same? I'm just, with this normalization, I'm just trying to understand how to interpret it.
So great question. And what it means is that there were no types of patents, the way I've broken out these four groups, that were significantly different from the average impact of normal inventions invented in homogeneous cities. You can see this is impact relative to normal homogeneous cities.
Okay.
And that's a flat line because that's all in, if you look at this model, right, that's all in the constant of the model. So it's all measured relative to that group. That's my baseline group. And so I can't say, that there was nothing impactful, but that just novelty was not important then. And in particular, novelty in big cities was no more important than incremental inventions. So it's still, to me, speaking to like that there was just a different mode of invention during the middle of the century.
Right, got it. Thank you.
Hey, Chris, can I ask a quick question?
Yeah, absolutely.
So I'm going back another 100 years to railroads and the history of the development of technologies in railroads. This is the work of Albert Fishlow and a bunch of others. And Fishlow, I think, argues that incremental inventions in the end are more impactful than novelty or breakthroughs. Mm-hmm. And I think he's thinking of their cumulative impact over time.
Right.
So then I'm starting to think about what's going on in the graph, and it's really maybe also going back to the methods. If you have a whole bunch of incremental inventions that in themselves, then by definition they're not that impactful, but together. I'm trying to figure out how a series of, I guess, if they're incremental inventions, they're not really introducing novel subclass combinations. Mm-hmm. But it's possible that yikes! What am I? I'm struggling to get this out. But what I'm thinking is, if you have a bunch of incremental inventions that are not really introducing anything new, yet that they're cumulatively important. But I'm not sure if they become somehow more important because a breakthrough invention comes along and actually combines all those incremental pieces in a new way. You know, so I'm trying to distinguish between the cumulative impact of lots of incremental inventions from a series of incremental inventions being produced, which perhaps allow then a novel invention to come along and generate a new combination.
Yeah, so that's quite interesting, and of course I can't get to all of that in a single project or in a single talk, but I think there's some empirical difficulties with trying to pick up cumulative impact of incremental inventions, in that the incremental is kind of setting a baseline, and so if you're looking for like kind of impact relative to some baseline, it's those incremental inventions are kind of going to be swamped out. It is going to be the case, as I kind of look forward in this and I start to look at which novel inventions are most impactful as a function of how much prior knowledge they build on. And I pick up those novel inventions are the most impactful ones. So I'll show that in a later chart, which seems to be a little bit of what you're going at with, like there's the stage was set for the breakthrough by a lot of incremental inventions that came before it. Yeah. And that breakthrough helped bring them together.
Okay.
So we'll look at that chart. I think that's about 2 charts away, and that might be, I think we can kind of read between some lines to think about that kind of story as well.
Chris, are you controlling for the year that the class was created?
I am not controlling for the year that the class was created, but I will. I've made these charts also using class fixed effects, which will control for the average. The average impact of a given class, and the charts are quite similar. I
mean, that you can get it from the USPTO lists, like the year that they've created classes like as recently as the 90, actually probably more recent than that. But basically, not every patent at every point in time has an equal opportunity to be in so many classes, and that's just talking classes, not even subclasses. So if that's your definition of novelty, there could be a time problem there. Does that make sense?
Yeah, so I have to think about that. Let me
assume there are only 100 possible classes from 1900 to 1920, then there were classes amended over the period 1920 to 1930. So those patents, in that second window have more opportunity based on the definition of novelty to be novel than the early ones. So what this graph could be showing is an exhaustion of combinations more so than of novelty, unless you control for the year that the class was introduced.
That's a very interesting point. We should talk more about this on the side. I think that the way the Z-scores are set up, but I'm not sure, and that's why we should talk about it a bit. I think that the way that they're set up is going to kind of account for that, because you can only have an atypical combination according to Z-scores if the individual elements have been used many times in the past, but haven't been used together. So I think that kind of expected value is going to be correcting for some of those shorter histories of classes.
Okay.
But I think it's definitely it's a very interesting point. It's something we should talk more about then on the side, because there might be something there, so we should talk about it.
Sounds good.
So just to add to that, I think somebody said in this seminar before that classes get reassigned if new classes are introduced. Not that I know anything about it, but that might be something to look into how this works in practice. Because I think that is really a problem. If you have something really new and there's no class for it yet, then that's a problem.
Right. Yeah. So that's something we can chat more about and stuff. I'll keep going ahead, and maybe we come back to this in Q&A afterward.
Hey, Chris. Just really fast, in answer to I think the really important point that Ryan just made. When we do look at the data and the combinations used, it's pretty clear in the data that an increasingly small share of all possible combinations are used over time. I mean, I think your point is a really good one, but well, I guess depending on how many classes we're talking about, there really isn't a limit. You know, there's no limiting factor when these combinations, some of them get exploited because there's so many others that haven't been exploited.
Gotcha. Yep.
So maybe we come back to this at the Q&A afterward or something.
Yeah, sorry.
Oh no, great points. So I'm going to hop into this. So what I wanted to show now is, okay, so basically we have this geography of breakthrough innovation at the end of the 20th century. It's breakthroughs are happening in knowledge diverse cities toward the end. That's, I think, very clear from here. Now, the next thing that I wanted to show you is what I've done here is decompose patent type, not just by what their novelty and the knowledge diversity of the location, but now we also have multi-locational patents. So the green line are novel patents invented in 2 or more knowledge diverse cities. And I think this is a red line here for novelty invented in a single knowledge diverse city. And we see that that departure is driven entirely by multi-locational patents. So it's not just a story of agglomeration. It's not just a story of scaling or spatial concentration in knowledge diverse cities. Really what we have now is that inventors are collaborating with other inventors that are also in these kind of highly knowledge heterogeneous environments. So what we want to do then is take stock of all the empirical information we've just looked at, and we want to start to interpret why are these outcomes happening. So to offer some kind of interpretation about what's going on in the late 20th century in terms of this geography, what's driving it, right? We need an explanation that's able to explain why breakthrough inventions in the late 20th century are increasingly invented in knowledge diverse cities, by multi-locational teams, and in particular, by multi-locational teams where all cities reside in knowledge diverse cities, right? It's just this like big city, many cities, knowledge heterogeneity story we're seeing empirically. So this is the explanation that I'm going to push forward a bit, and we can talk a little bit more about it. And to try to formalize the identification here a bit more is something that I really look for some, your feedback on. So my explanation has 3 parts. The first is that inventors increasingly need to draw on large bodies of existing knowledge to create impactful novelty. I'm going to show you some empirics that substantiate this statement. But what this is, and like I said earlier, this seems to suggest that it seems to be conflicting that you would need a lot of existing knowledge to introduce impactful novelty. But I think that we can think about drawing on existing knowledge to kind of embeddedness in the past and the introduction of novelty, not as mutually exclusive aspects of an invention, but something that's more orthogonal to one another. And it's that you can be ingrained in the past, embedded in the past and drawing on previous knowledge, but still see ways to combine things in new ways. And that's what I think is explaining the breakthroughs today. Earlier on in US history, it looks like the breakthroughs were more, based on basic insights and not as embedded in past knowledge. The second part of the explanation is that inventors increasingly are able to collaborate effectively at a distance. This was largely materialized in the charts that we already saw about multi-locational patents predicting high impact novelty. The third part of the explanation is that inventors are not able to source knowledge from locations where they do not have collaborative partners. So there's been a persistent advantage of geographical proximity for sourcing knowledge. And what I'm kind of going to be saying is that geographical friction is only alleviated when you set up collaborative partners in different locations. So you need to have people on the ground. So let me start with this first point about inventors increasingly need to draw on large bodies of existing knowledge to create impactful novelty. This is what I look at in this regard. What I've done here is, once again, we have impact on the y-axis, and this is normalized as in those earlier charts by those number of classes times time fixed effects. And I've classified patents based on whether they're novel or not, but also the extent to which the number of knowledge-based parents they have according to my technology tree. So patents with many parents have, well, many knowledge-based parents in the tree. I'm using a binary cutoff here to be able to show just 4 lines, but this also works if you define that as a continuous variable and run a regression model on it. And so what we see here is like that uptick that happens in the 1960s, that's really happening with novel patents that have many parents. So if you're introducing novelty today, it really, really, really helps that you're more strongly embedded in past knowledge. You can think of, if knowledge flows experience friction moving across distance, this uptick in that starts in the 1960s is going to induce breakthrough invention to be created more and more in knowledge diverse places where those possible parent elements of knowledge are accessed through face-to-face. The second thing that I wanted to share in terms of this inference is the advantage of presence in the location where knowledge is. So again, I'm dividing patents into 4 groups, and I'm looking at the patents for a given patent. I'm looking at the knowledge that they draw on, and I'm looking at the extent to which that knowledge is embedded in patents that were invented in the same city where the given new invention has inventor team members located. So a novel patent that's sourced locally, I'll give you an example. Let's say that Carolyn and I collaborate on a patent. Carolyn's based in London, I'm based in Los Angeles. If we invent something that's novel, we should be, if we're sourcing locally, it means that we're sourcing knowledge from either Los Angeles, prior inventions made in Los Angeles, prior inventions made in London, or both. If we're sourcing knowledge that's non-local, we might be sourcing knowledge that's from Dublin, where we don't have a team member on the ground in. And so what you can see here is that green line is always well on top of the red line in this case, meaning that novelty is always benefiting throughout the entire time period by sourcing knowledge where you have team members. If you're a little bit worried that the green line starts to, it looks like, be dropping down towards the x-axis towards the end, it's actually quite robust. Here I've thrown in class fixed effects, so something we talked about, and it's going to remain up high. So basically there's been, according to my evidence, no, the advantage of geographical proximity for sourcing knowledge has remained robust across the 20th century. The only real change about moving across geographies is that collaborations across distance seem to be easier now. So putting all of this together, I wanted to offer kind of a couple of ways to synthesize that information. And so the first point is that if you think about the extent to which breakthrough invention is spatially concentrated in knowledge diverse cities, the way I'm kind of thinking about this inference is it's really a function of the quantity of knowledge, of prior knowledge required to make a breakthrough. And according to this chart, that value has been raising over time. So this is going up. And then the difficulty of sourcing knowledge across distance has remained constant. So it's not, I think, there's literature that will talk about how knowledge is becoming harder to move across space. That's not what I find, but I just find that it's just as hard as it used to, but you just need a lot more of it. And that nonetheless leads to an increase in the spatial concentration of breakthroughs. But then thinking about these multi-locational inventions, if collaboration across distance is not particularly costly, or if that collaboration has dropped over the course of time, basically multi-locational teams will organize to source knowledge that is dispersed across space. So that's like the team response to the increased need to build on prior knowledge to make breakthroughs, is instead of sourcing from places that you aren't, you get people who are in those places. You make these non-local teams. With that, I'll extend into the acknowledgements. Let me also especially thank Frank van der Wouden on this. He provided data on multi-locational inventions before 1975 that was really helpful to check the robustness of all of this going back in time. And with that, I think I'm done. So I can take any questions. So thank you.